This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known. So welcome to the Math Map Book Club, where Dr. Kirsty Gilpin, my favorite polymath, leads us through a variety of mathematical topics to help parents prepare for the Classical Conversations curriculum, the Math Map. So welcome, everybody. It is July 15th, 2026, and it's great to see the familiar summer faces. And of course, anybody is welcome to attend any Wednesday at 1 p.m. So thanks, everybody, and thanks, Kirsty. What do you have for us today?
Well, we are today going to talk about adding and subtracting fractions because everybody loves fractions after last week, right? I have enticed everybody to realize the joy of fractions, and you're all so excited now to add them and subtract them. So first, I wanted to make us all think back. Those of you who have been coming all summer or have watched the recordings, remember that we started by talking about units, right? And we talked about that when we're working with math, that we have to know what our units are. Usually, if there's nothing written, our unit is 1, which is why sometimes 1 is called the unit or unity, because there's 1. So if I see the number 5, it can mean 5 ones. When we think about fractions, we talked about this, but I know it's been a little while. The fractions actually are different units. They are not ones anymore. So let's read aloud. This is always what I think is the absolute secret to demystifying fractions, is to say it out loud. All right, so when we see 3/4, I just read it. So somebody go ahead and read that top line.
3 over 4?
Yeah, 3/4. Or how would we say that if we wanted to be able to say using our ordinal numbers on the bottom, like the TH numbers?
3/4.
3/4. So if we read that as 3/4, what is my count and what is my unit?
3 1/4.
There you go. So I have 3, that's my count, and fourths is my unit. That's what I'm counting. So how about 3.1 over 7? How would we read that?
3.17.
3.17. Yep. So what's my unit?
3.1.
Oh, no, that's my count. That's how many I have.
Oh, sevenths.
Sevenths,
Mm-hmm.
right? So those TH numbers those are the numbers that are telling me what my unit is. And so now it still works even for our variables. And I want to include this so that all of our families see that as we progress through the domains, these ideas apply across the board to all these different kinds of numbers and all of these different types of expressions. So anybody want to take a stab at how we could read that bottom one?
The square root of 3x.
Yes. I don't know if anybody else would read it that way, but that's exactly how I was thinking about it. Yes. And we can write that as multiplication to be really explicit, that we mean we have 3 of 1/4 and 3.1 of 1/7 and the square root of 3 of 1x, right? It's really important that we know what our units are, because when we're comparing or combining, we have to have like units. So are 4s and 3s like units? No, right? If I was counting up by 4s and counting up by 3s, and I said I had 10 4s and 3 3s, I can't add those together, right? So are fourths and thirds like units? How about x and x plus 1? Are they like units?
No.
No. So would their reciprocals, the x and the x plus 1s, be like units?
No.
No. How about a and a squared? No. So eighths and a squareds, right? So I think this is just kind of a fun thing you could do with your students if they are struggling to identify like units. Is just play a game and say, are these two things alike? And mix up and say, have some things that are, right? Are mugs and mugs like units? Yeah, I could do that, right? But mugs and glasses, they're not. So just playing with them and seeing that when we're talking about units, right? This is going back to our first session this summer. We're talking about the things that we're counting or scaling or measuring, that's what we're talking about. And so we need to make sure that we're looking at like units before we can compare or combine.
So, Kirsty, would you say that x and 2x, they're not like units if they're on the, I mean, we can't add them like that as a fraction, but when you get to like other kinds of expressions, you could add 2x and x together.
So I would say if I said something like this, I have three, there we go. I have 3 x's and I have 4 2x's. Right? Can I add the 3 and 4?
No.
No, because my x and my 2x's are 2 different units.
Right.
However, could I take that expression and rewrite that as 8 x's? It'll show up at some point.
Right. Now you
Right.
can,
That our associative and commutative laws would let me rewrite it. So now I've converted my units, right? And we could actually write that as a unit conversion because I could say that I have 2x and I want to convert this to x's. So if I multiplied that by 1/2 over, is that right? Yes. Or 2. I could have done it, I did it a hard way. I don't know why I did it a hard way, but let's say that we multiply by 1/2 over 1/2. This becomes x over 1/2. If I multiply that by 4, right, then I get my 8. So I can still I can either recognize that the way math works is that I'm using my associative law, or I could actually show a unit conversion from 2x to x, which is going to let me see that I can now multiply that by 4 and I'm still going to end up with 8x. I just wanted to point that out, that it still follows those same rules of converting our units. But we had to do something. And so the key idea there is that I had to do something there before I could make a sum. Right? When I'm thinking about units, that's what helps me know, oh, I have to do something. And it's actually this idea of the units and what is it that I'm adding, subtracting, multiplying, and dividing that gives us our order of operations.
Something I want to add is like, you knew what to do to start, and you hear that from young people. I don't know how to start the problem. Like, I don't know what the first step is to try to make this right. So I thought of this, the homeschooling parents are really into genus and species in our logic class. And so maybe playing a game with your children where you say something like, we can't add apples and oranges, but what contains apples and oranges? Fruit. So I can't add, frogs and lizards, but what contains them? They're amphibians. Well, you can't add the third and the fourth, but what contains them? 12. Right? Start making that a comparison for them.
That's very cool. But aren't lizards reptiles?
Yeah, I think I said that wrong.
Sorry, just little details.
Well,
All
yes.
right, so in a
why
minute,
not?
you're going to see my screen, and I just want to let you know that Lee did not actually come read my screen before she came up with the same examples for some of these, but hey, it's all good.
Yours will be
We're all-
right now.
We're on the same wavelength. That's what matters. All right, so what we need to remember is that all of our fractions are convertible units. Going back to, right, we're going to talk in a minute about converting units and when we do that, and as Lee pointed out, remember, we cannot convert outside of our dimension, right? So I can't convert a linear measure to a square measure to a cubic measure, right? I can't convert something that's 3D-ness. So I couldn't convert lizards and tadpoles, whatever umbrella we come up with. There's no way that I could convert those to feet and inches. Right? So not everything is convertible, but all of our fractions are. The key idea and sort of the authority for this is that if I have my fraction, my numerator over my denominator, right? If I have my fraction, I don't know if it's my computer that's slow or anyway, here's my fraction. If I multiply it by an identity fraction, same numerator, same denominator, I'm calling that an m as my multiplier, then I end up with a fraction that is n times m or m times n over the fraction that's m times d. And notice that the value doesn't change. The expression does. And I've changed my units because I've changed from my units being d to my units being md or m times d. But the value is still n over d. And that is the big idea behind converting fractions. Now, when we look at, I'm going to do this really quickly for us, if I can. All right, so remember that this equals 1. And it still equals 1 here. And there's two ways that we can think about that. We can think about having a common, and I was going to change this and I didn't, but multiplier for my numerator and my denominator. Or I can think about it as a conversion factor. Most of us probably think about having that common multiplier. So where we take our 1/4 and I multiply by 3 over 3 to get 3/12, and then 1/3 times 4 over 4 to get 4/12. And that hides a little bit of what's going on. It's correct, right? It's a correct thing to do, but we've been taking a look at this other way of writing it. So for two reasons. One, understanding that we can convert our fractions just like any other unit, I think pulls us from where we had these discrete and different ways of dealing with fractions to other numbers, and helps us to see that what we're looking at is consistent across all of the things, everything, whatever it is that we're trying to add. Fractions work just like every other unit. When we think about that and we think about this idea of a conversion factor, what we end up with is that we change our identity fraction a little bit, because we still have an identity fraction. This is still equal to 1, but now I'm actually showing all of my factors, not just the missing factor. And I see what this is going to be my new unit, shows up here. So I can actually see how I'm changing from fourths to twelfths using an identity fraction. And that may help your students. Even if they eventually get to where this is their shortcut, I think using this idea of fractions as a conversion factor is going to help them. So that's why this works. So let's look at our next slide. So here we go. So let's talk about adding fractions. And again, I want you to read these out loud. And so you're all muted. So you can go ahead, read them out loud, and then combine. And then you can just take turns telling me what's 3 apples and 4 apples.
7 apples.
7 apples.
Three A's and 4 A's or 7 A's.
Yep.
Three halves and four halves are 7 halves.
Mm-hmm.
And 3
Three
seconds.
halves.
Go ahead, India.
I was going to say 3 halves plus 4 halves equals 7 halves as well.
Yes, exactly. Now, for our students, if they saw the words half, right? If they saw 3 halves and 4 halves, most of them probably don't even think that they're thinking math, and they would just say, well, it's 7 halves. As soon as we write it as a fraction, I think a lot of us sort of go, oh, what I'm doing, I've got to think about my math rules, right? What's my math rules for fractions? Well, if they have the same denominator, I add the numerator. And that's what we do, right? We stop thinking about what we already know instinctively, and we go into, wait, my teacher taught me this algorithm. I need to know the rule. How do I do this? So I really want to encourage everybody to read aloud your fractions, even if they're common denominators, even if it feels like this is pretty simple for your students, read them aloud. Because if we read, we've been saying this all along about the math map. Read, 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 read. We're still saying it because when we see the fractions, we can sometimes and if we read it aloud, all of a sudden we hear the language and it makes more sense to us because we use words like halves and thirds and quarters all the time. Right? How long do I have until I go to bed? About a quarter of an hour, about half an hour. Right? We use that a lot of the time, and our kids understand what we mean. So if we connect the idea of the symbols to the words, I think that we're going to help demystify some of this. And again, as we talk this summer about what are the patterns that we're helping with our students, playing a game just like this, where pick 2 numbers and I just keep adding those same 2 numbers with lots of different units, is going to help them go, okay, this is what I'm doing. Whatever my unit is, it doesn't matter. I'm just adding my number. Now let's take a look at why. So this is less for your students and more for you, because a lot of us grew up hearing that we were just told if they're common denominators, add the numerators. And we may not always understand why. But I think if we see the why and we see all the steps and we go, okay, this is just what we've been doing everywhere else, that it'll help us to know what questions to ask our students in order to help them see some of these patterns. So I've made this both addition and subtraction just because it works the same way. So if I have 3 halves and 4 halves, right? If I write that as with my units, I have 3 and my unit is 1/2, 4 and my unit is 1/2. My units are alike, so I can keep going. What I'm going to do next is undistribute the unit. Right? So if this was 3 halves minus 4 halves, this would become 3 minus 4 times 1/2. If it's 3 halves plus 4 halves, this becomes 3 plus 4 times 1/2. All I did was undistribute that unit. So now when I see that, I can see, let's look down here, I've broken them out. So I have, if I'm adding, 3 plus 4 becomes 7. If I'm subtracting, 3 minus 4 becomes -1. Then I can multiply again, and that'll let me express it as a fraction. And I end up, if I had 7 halves, right, I can write that as 7/2 or 7 halves. And -1 halves becomes -1/2. So notice that this is the step here where it breaks down if we don't have common units. Because if I had a half and a fourth, I cannot undistribute. So that's why that I keep coming back to that distributive law being so important for us to understand, because that's the very nature or the very basis here for why you can or cannot add common, you can add, or uncommon, you can't add units. Any questions on this? All right, so now let's think about which of these units could be converted to a common unit. So we came up with fruit. Is there anything else that we could change apples and oranges to make them alike?
Fruit.
Bananas and peaches?
Okay, so we could come up with
Is it
other
wise?
but thinking in terms of like the genus and the species, what else could be a genus for oranges and apples other than fruit?
Round.
Juice, cats and dogs.
Okay,
Oh.
so fruits that you could juice, that's I like that. So juicy things, round.
Fruits from a tree.
What was that, Lee?
Fruits, things that grow on trees.
Things that grow on trees.
Oh,
Food.
I think I don't understand the question.
Food.
Things that will decay.
Things that will, oh, I like that one. That activity is really going to be helpful for, right, just thinking about all the things that you could integrate, right, beyond mathematics if you're asking your students to identify, right, if here's my species, what's my genus? How about A's and B's?
Oh.
Can we convert those to a common unit?
Letters?
They could be letters.
Could you call them literals? Is that a
They could be literals. Now, if they are literals, can I combine them? Can I convert them if they're being used as literals in an equation?
no?
No. So this one's kind of a tricky case because I could be saying, okay, I just want you to go and look on that page, count up all the A's, now count up all the B's. How many letters did you have between them? Right. So there I've made a genus and a species to combine. But if I had my equation was 3A plus 4B equals 7, can I combine those or in any way? No. So there's some tricky ones there that you could have a great conversation, I think, with your students to help them those older students to start discerning the difference between what can be converted and what cannot. And then we've already kind of answered this question. How about halves and thirds? Can they be converted to a common unit? Yes. Whether we say it 3/2 or 4/3, we see that we can convert those. And so we're going to take a look at that. Okay, so here is an example. So 3/2 plus 4/3. And this is using the idea of converting the fractions. So I have 3/2 and my conversion factor here has a 2 and a 3 because I need my factor. So I have a 2 and a 3. If I have a 2 and a 3 as my new unit is 2 times 3, then my numerator has to be 2 times 3. Right? Then I have 4/3. It had the 3, right? It had the third, but it also needs a half. It has to have both units here in my new units. So it's going to be 3 times 2. If my denominator is 3 times 2, my numerator is 3 times 2. Then notice that what we can do is, and I wrote it here so that you could see that I've canceled out my 2's. I'm going to change my pen to red so we can see that so it looks clear.
Kirsty, can you put the box around the identity fractions?
Yeah.
I think that makes it easier to see it.
Okay.
Well, unless everyone's past that point and we all see what you're saying, you can.
No, I could do that. Here we go. It'll show up in a minute, I hope. Let me get my pen and show you how we're going to. I can cancel my units just like I do, right, when I'm doing inches to centimeters or anything else. And we say, right, find your like factors. And so my 2's are alike. In this product, my 3's are alike. And so I'm left with 3/1, times 3 over 6, because 2 times 3 is 6. Then 4 over 1 times 2 over 6. And if I multiply those, I end up with my 9/6 plus 8/6 is 17/6. So take a minute.
Why don't you cancel out the 3 over 3 in the first one?
Well, because remember, I'm trying to change this to sixths. So I started with my 2, and I want to change this to a common denominator, to a common
Got
unit.
it.
So if I cancel out my 3's, I just get back to where I started.
Gotcha.
Yeah, I think all this is easier to understand when you get to 3 of the fractions. Nicole, I did the exact same thing the first time she showed me this and I wrote it out. I just started canceling what I wrote.
Mhm.
So let's go ahead, let's do another one. And then I'm going to give you a minute to think through what you would do. So let's do one together. So hopefully my pen will work. So we've got 3 halves. And I need to have a common unit. So that common unit needs to have the 2, the 3, and the 5 in it. So I'm going to look at the product of those 3. If my denominator is 2 times 3 times 5, my numerator has to be 2 times 3 times 5. And I'm just going to use a red box for the sake of time. All right, so now we've got our 4/3. So what is my new unit that I'm trying to get to?
3 times 2 times
2 times 3 times 5. So my identity fraction is going to be the same. Once I know what that fraction is, it's going to be the same for all of my terms. Now, I'm showing you a pattern here, and in a minute, I'm going to show you why this works. But I'm showing you a way that will work for all of your fractions. Okay. So there we go. So now let's think about going back and seeing how we can eliminate our original, right? So I have a 2 and a 2. What do I have in common in the next term?
3 and 3.
3 and 3. And in my last term?
5 and 5.
5 and 5. So what is my new unit?
30ths.
30th. And so now I can go back and I can say, okay, well, I have 3 times 3 times 5. That's 9 times 5, that's 45. I'm obviously not showing you all the work. 4 times 2 times 5, that's 8 times 5, that's 40. And 2 times 2 times 3 is 12. And I end up with 85, 97 30ths. This method will work for any number of fractions with any denominators. But I'm going to quickly go through the next two because I want you to see the comparison between two ways of thinking about it. The first is probably how I would let my younger students who are still exploring this idea think about it. The second is a little bit more elegant and what I would hope that my older students would be working toward. So again, I'm going to look here, and even if all you did with your students was say, what is going to be my conversion factor? My conversion factor could be 2 times 3 times 4, because I'm going to use all of my denominators. And then it's an identity fraction. So my numerator and my denominator have to be the same. And so I would have 3 halves times that, 4/3 times that, and 1/4 times that. So if we did that, I'm going to do this quickly here. It's going to show up. There we go.
Okay.
Okay. What are you not liking?
I think I'm not, I think I'm just trying to think through like what happens when you have like if your denominators are like 2, 4, and 8. Would you,
I'm
because
going to show
my
you
brain
that.
is still like,
So let's finish this one. This is where we're not thinking about any of the factors of our denominators. We're just looking at our denominators. And so we're still going to see that each of these is going to simplify. And what am I going to end up with? I'm going to end up with 2 times 3 times 4, which is 36. And 4 times 2 times 4, which is 32. And 2 times 3, which is 6. And what's my new unit?
24.
24. Now, if I sum this, I end up with 68 plus 6 is 74 24ths. Can I simplify 74 24ths?
Yes.
Yes. I can simplify that to 37 twelfths. So if I use all of my, if I don't have what we call relatively prime denominators, I'm going to end up with a fraction that can be simplified further. And this is what you were asking about, Nicole, because what is true about 2 and 4?
they share the
Two,
factor of
four.
2.
They both have a factor of 2. So if I'm seeing what's happening, right, I'm following this and I'm seeing what's happening, this is the pattern that you're not going to see in 4 examples, but over time or practice that your students could start to see, is I need a 2, I need a 3, but when I get to 4, I might go, well, I already have one factor of 2. So what else do I need? I need
2 more factors
The
of 2?
factor of
how
2.
many
Yeah,
more factors of 2
one
do I need? Just one.
just one more.
So 4 is 2 times 2. Well, I already have 1, so I just need one more factor of 2.
Okay, so you got to help me understand how I would explain that because
Nicole,
otherwise I would just do 4.
so here's what's going on. If you use this method, so you know how to reduce numbers. So you or I would go back to our old fashioned stack the 3 fractions up, quickly convert them and add them up. But that's because we have an intuition for numbers. So when you're trying to teach a child who doesn't recognize that 4 is part of 128, and right, and so this way they can multiply. They can do the same algorithm every single time doing this way. It'll never change.
Gotcha.
Right.
But
Once
what,
we're good at noticing 12 and 4 and 3 are all part of 60, we just ignore it and we go to the simplified version.
so I think my question here though is it looks like I could do 2 times 3 times 4 and just do the longer version, right?
Yes.
So
First.
That's what we just
I
did
could do
in
that.
the last
Yeah,
row.
which is what
Mhm.
yeah, that's what we've been doing. But now this one, 2 times, I can just imagine my kid because I'm doing it, even though I know the answer. 2 times 3 times 2 is not the same as 2 times 3 times 4. So why exactly are we saying you don't have to do 4? Is it just,
I'm going to show you in a minute the math behind this, and then you're going to go, oh, okay, I get it now. With your students, right? What you can ask them, right, is if you do lots of that third line and then they have to simplify, right?
Mhm.
Go, okay, do you think there's a way that we could do this without simplifying at the end, right? Is there a way we could do this without having to simplify at the end? So what are we doing? We're saying we have to have the same factors in each one.
Mhm.
So, oh, wait a minute, I actually am doubling up because I already have a factor of 2. That's where you don't start at the bottom line, but this idea of classically learning where we give them lots of examples And then we say, well, what did you notice? What did you see? Can you compare these? Can you compare these two? What do you think is happening? And don't feel like you have to explain this on day 1 or day 10. It might be 3 years on that your student suddenly goes, well, this is stupid. Why am I doing it this way? Because I always have to simplify at the end. Couldn't I have just taken out that common 2 at the beginning? Right? Like it might take some time for them to see that. And that is okay. Right? Because we've been trained to think we have to jump straight to the most elegant or the reason why, or right, that okay, I'm going to tell you why.
Stop.
And what we want to do is slow down and let them come to that discovery, right? That we have this ability now to say, look, this is a way that's going to work, yes, but I want you to always be thinking, is there a better way? Right? That
And
is
then
there
let
a better
them
way?
discover that. That's amazing. Oh my gosh.
So now here's why that works, right? That's why I said this is the testimony. This is why what we were doing is working. Because when we think about our least common multiples, that is defined as the smallest number that has all the prime factors of the given numbers,
Yes.
right? We've talked about that. And so our least common denominator is the least common multiple of the denominators. So in the first case, 2, 3, and 5, right? They're all prime numbers. So I didn't even really have to factor them because I look at them and I go, well, those are all prime numbers. So I can just multiply those together and I don't have to worry about it at the end. But if I see 2, 3, and 4, now I might want to go, okay, well, 2 is prime. So it's either 2 or 2 times 1. 3 is 3 times 1 because that's prime. So 4 is 2 squared. Oh, for my least common multiple, I just need the prime factors, right? And I don't need without duplicating. So my 2 squared includes my 2. So I only need the 2 squared. I don't need the 2 as well because that 2 is captured in that 2 squared. So I'm going to need my 2 squared. Sorry, I just realized that. Here we go. Right, I need my 2 squared. That includes my 2, so I don't need that. I only need my 2 squared. And then I need my 3 because I need to make sure I have that. So that's where I end up with my 2 times 3 times 2 or 3 times 2 squared is 12. Can you show your students this and jump to this? Absolutely. But it's okay to give them something that works. And this we've talked back and forth all summer about you can show them right the why and see that, or you can let them work through an algorithm. What you don't want to do is say, here's an algorithm and stay there. That it's okay to go back. It's okay to go back and say, here's an algorithm. This will always work. Anytime you want to multiply fractions, this is always going to work. But you don't want to always stay there. You eventually want them to be able to go, this is why that algorithm works. So it's okay to start with the algorithm and go, hey, and over time, and when I say that, it can be multiple years. Over time, we want to end up with them making the connection between these ideas. Or you can start here and say, okay, well, how do we put this into practice to actually do this? So either one is okay.
So something I think is important is like we just use little numbers for little children, but as a mathematician, if you can't really quickly say that 52 and 17 have something in common, then you're in trouble when you're trying to factor because you're going to multiply really big numbers in order to try to find out that common denominator. So Kirsty's method on the other page, if she used easy numbers, I did one with hard numbers the other day. I got into the thousands, but the answer was right and it always worked. And I never had to go get a calculator to do it. So there's other advantages to what Kirsty showed us. It's just not the fastest way, but it's the correct way, I think, to do this.
So isn't, correct me if I'm wrong, but when we were going through, I feel like the math map this year, there was a portion on factoring that really confused everyone seeing it the first time. But essentially it was this, and then we were told at the end to take the highest prime number from each of the numbers, and
Yep.
that would have given you the 4, and you would have discounted the 2 because you were going
Yes.
with the highest value of that.
Yep. That's exactly what you were doing. Yep. I know that makes Lee really happy when she hears people going, hey, I'm making a connection between what's in the lesson pages.
But I think, Kirsty, you know, why you and I struggled, we rewrote that lesson so many times over so many years because we knew we were intuiting how to figure out what the factors were. And Kirsty came up with how to be sure of what the factors are. And that's the difference.
So that makes me think of like, well, that makes me think of like if you, I know this is gonna sound weird, but like if you're lifting weights and you lift 5 and then 10 and then 15 and 25 and then 100, and then you've gotten to the place where your muscles can lift 100 pounds, and then somebody brings in a machine where the machine can now lift the 100 pounds really easily. And you go, well, why did I have to go through all this stuff to lift all these weights to get to where I could lift 100 pounds when you could have given me this machine that gives me leverage to lift 100 pounds? And at that point, the goal has changed, right? The goal for you growing your own muscles is so that your body could be bigger, but the machine is for something to be lifted, right? And so now you have two different goals. So in my mind, I'm thinking, our kids are going to be like, why didn't you just show me the shortcut first? And the answer is because doing it the long way is developing your brain, and doing it the short way is just getting the assignment done. And the goals are different.
I like that, Nicole. All right, I have to be done a couple of minutes before 2 because Babs and Lee are both starring today on the Latin Book Club. But I really want to take a look at something that can trip us up. Because as Lee pointed out, these are all fairly simple fractions that once you start dealing with fractions, you kind of intuit a lot of what you're doing with them. But mixed numbers can cause us all kinds of problems because of this hidden addition. And notice that we have 3 ones and 1/4. The ones and the fourths are different units. That is why we cannot add them together, and that's why we write them as 3 and 1/4. What we're really saying is I have 3 ones and 1/4. I have 2 different units in one mixed number. So sometimes it's a lot easier to take and convert those in order to combine them. And so that's what I did here. So in this case, I know that my 3 is really 3 over 1. And so my units are going to be 1 times 4. I omitted the 1. I just wrote my 4, right? So here's my identity fraction, my 4 over 4, plus 1/4. I don't have to change that because it's already in fourths. And so I end up with my 12/4 plus 1/4, which is 13/4. I will tell you that most mathematicians only deal with improper fractions because of this hidden addition. Now, for our students, because in our real world, right, if I was to tell you that I needed to cut a board, I wouldn't tell you that I needed you to cut the board 13/4 feet. All right, I would want to tell you I need a board that's 3 1/4 feet. So help our students to see that what we use mixed fractions, they're very, very useful for us communicating about numbers. But especially as they get older, it is okay to use improper fractions because it eliminates this issue of this hidden addition. Now, when we add our mixed numbers, if we remember that we have addition and addition, notice I have 3 plus 1/4 plus 2 plus 1/3. So now my associative and commutative laws say that I can take my ones and combine those, and then take my fractions and combine those. And so my 3 plus 2 becomes 5. And I don't have to worry, unless I want an improper fraction at the end, I don't have to worry about converting that 5. This is the easiest place with mixed numbers. I only have to worry about converting the fractional part. So I did that separately to see that it becomes 7/12 and my answer becomes 5 and 7/12, right? Adding mixed numbers is the easy spot when it comes to mixed numbers. Now, we could have taken our 3 1/4 and our 2 1/3 and converted both of them. And then when I come to making common units, notice the whole number is being converted. And so I end up with 13/4, and here's my conversion factor, 4 times 3, and then 7/3 with my conversion factor, 4 times 3 or 3 times 4, and that'll simplify to 67/12, which if I converted back to a mixed number would be 5 and 7/12. So I get the same answer either way, right? It's just, where do I make that? What am I converting, right? So with mixed numbers, there may be an argument that it was easier to add them in their mixed number form. And I'm okay with that. But I wanted you to see the comparison of both. Now here's where it kind of breaks apart when we want to subtract our mixed numbers. This is where we need to make sure we remember that we have a sum, right? These are sums and we're subtracting. So now, and I didn't write all of my steps out here because I was running out of room. If I distribute my negative through, I get -2 and -1/3. Then I can use my associative and commutative laws to rearrange, not the right, because thinking that I'm keeping things in the same like linear order, like I didn't do 2 times -3, so that's why I can do this. I have 3 minus 2, and then I have 1/4 minus 1/3. So we can sit here and go, well, that part was easy. That's 1. Now let's go ahead and do our fraction work down here for 1/4 minus 1/3. I'm going to convert it to 12ths, and I end up with -1/12. So it becomes 1 and -1/12. But now I have to do some more work because I actually have to deal with this negative. And so I end up with 12/12 minus 1/12 equals 11/12. I think personally that was a lot of work, and there was a lot of places where I could make an error, right? There were a lot of places to get slipped up and make an error in subtracting my mixed numbers. So let's take a look now. We might go, oh, this one was a lot better doing it with improper fractions, because I could take my improper fractions, and as it simplifies through, I never ended up with that weird -1 and -1/12, right? It deals with it itself, so I end up with 1/12. So I'm making an argument. Consider working with improper fractions. Sometimes they feel less friendly because that numerator is a bigger number that we have to multiply through, but it does eliminate some of the errors, especially for your older students. For your younger students, learning to work with mixed numbers and using the language of mixed numbers is going to be more familiar. But for your older students, especially, consider letting them use improper fractions because it will cut down on the places that they can make errors.
And what Kirsty didn't do, or show us, but she did, and you probably did too, is you said 4 times 3 is 12 plus 1, and 2 times 3 is 6 plus 1 is 7. To get your 13/4 and your 7/3. You can show the students those kind of shortcuts, but that doesn't teach them the fact that those are 2 separate units. It doesn't teach them how they're adding things. It doesn't teach them the identity laws that allow them to add it. So it's not that we're against these shortcuts, but this is why we teach arithmetic so badly. Then we get to algebra and you can't use the shortcut because it's letters. You haven't practiced the process enough.
Would you delineate younger students and older students being like anything less than complex would be the younger students, and anything complex and above would be the older students?
Well, let's
No, I would say they're all younger.
Yeah, I would say maybe I'm using bad words. I should be saying your students who are less familiar and your students who
Yeah.
are more familiar. You might
Yeah.
have a 7-year-old who it just clicks. It just clicks in their brain and they're ready to start asking the questions. Well, what if? What if I did this? And you might have a 16-year-old who is still working through understanding that 3 and the fourth is 3 plus 1/4. And there's no judgment on the level of either one because we all have those different speeds at which we become familiar with things. But I would say it's more about a familiarity and a mastery that as they become more familiar and confident, that's where we start asking those questions. Why does this happen? Would it be easier if we did it this way? What would be easier, and introducing those things that way, I think is how I would go. So
And maybe not easier as much as simpler or fewer steps. Like say what you mean by easier as you talk to the students. That helps. And the other thing is what Kirsty started us off doing. This is a perfect example of doing it again if we had the time. Can you see how just reading across on one of these vertical, long horizontal lines will make it more comfortable for the student? Because this is a lot of math and our eyes don't practice this enough. So reading 3 and 1/4 equals on and on. Who cares if they can solve it? Just have them read it. If they can't read it, they can't solve it.
and along with that, Lee, right? Because I didn't do it because now it's working, right? But as they're doing it, say, okay, I want you to use I shouldn't have used green there, right? I want you to use a green marker and I want you to mark the identity fractions. I want you to use let me turn it on again. Maybe I want you to use an orange marker and I want you to circle the units, right? So here's my units that I'm changing to. So that way, as they're reading, you can practice the highlighting. It's not going to be the same highlighting colors as we would use for reading a book, but we can still help our students to identify the parts, right? Maybe underline each of our terms. Right, all those different things that, as we're close reading, we can close read mathematics as well. And depending on what your family is working on, building familiarity with, is going to depend on maybe what you want to have them highlight or underline.
Hey, I want to add as an aside, if you go to the Words Aptly Spoken, the one thing that we do in the literature courses is we just take a passage or two and we do a close reading. We're trying to show that no matter what it is you're learning, slowing down and looking at individual words and symbols is what an educated person does.
So if you want to practice at home, what does this look like, right? And last week we talked about the fact that you can do this over the summer. You can do this when you notice, hey, we need to shore up, right? That you can add this practice in at any point in time. And I've tried to identify some pre-practice. So what is it that our students need to be able to do before they jump into adding and subtracting fractions? Well, they need to be able to identify like and unlike units. They need to be able to read the fractions. They need to be able to identify the unit represented by the fraction, and then specifically be able to identify like and unlike fractional units. So that's just reading, that's just identifying, attending carefully. It's not actually adding and subtracting. It's just reading and attending closely and being able to identify what the parts are. When they are good at that, right? When they're confident in that and familiar with that, then I would say use some dice or some cards to create random fractions with common denominators. Right? So maybe you roll a dice and that gives you your denominator, and then you flip some cards to get your numerators and let them add and subtract. Then use dice or cards and create random fractions now with random denominators. So sometimes their units might be the same and sometimes their units might be different. And again, you're going to start by comparing the units, converting where necessary, then adding and subtracting your fractions. So there is an infinite number if you keep adding digits, right? depending on how many options you want. You could have an infinite number of problems, but there's thousands of exercises that you can create with dice and cards and let your students practice. And the more that they do, right, the more they're going to become confident and familiar. And the more that they do, they're going to start to see patterns. Right? And they're going to start to say, well, Mom, why do I always have to divide by 2 at the end? I don't want to have to simplify out a 2 at the end, right? So that's where I'm saying that if they do something and they see that pattern, they may pull back and go, hey, all right, can I make this easier for myself? And then next week, we are going to finish up our summer book club with multiplication and division of fractions. I think a lot of times it's easier. I think the addition part is the hard part. So this week was probably the hardest week. And then we will jump into next year where we're going to be using rationals and binomials to look at the lessons classically. Nicole, I'm really listening to you when you're like, how do I lead through this? We're going to really try to work together through some of these lessons. What are some of the questions that we can ask to help our students to make meaning? So that'll start on July 29th. And we are 3 minutes early so that everybody can get to the Latin book club. I know we didn't have time for questions this week. There's maybe 30 seconds if somebody has a pressing question. Otherwise, please email us and we will be happy to make sure that those questions get answered.
Thank you so much. These are always so good.
Thank you.
Thank you.
Thank you, Kirsty.